Well, at this point, we have finished our preliminary study. We now understand the four types of rigid motions, and now we want to seriously begin to think about symmetry. And the first object I want us to consider is simply a circle. Now, to think about a circle is sort of featureless, and we can't see whether we've rotated it or whatever we may have done to it. It still looks like a circle. So it's probably useful to draw something whose boundary is a circle but has something more interesting inside. And what I've chosen here is a $quarter, a standard coin with George Washington shown on the face of that coin. Now, one thing we can do, as shown by that arrow going off to the left, is that we can rotate it. So we can take that quarter and rotate it through a certain angle, and we can see that we've rotated it because, well, George, instead of looking to the left, is now looking up towards the sky. Okay, so we know that the boundary circle has been rotated, and the quarter came along for the ride. Also, we could take and we could reflect it. Now we know a reflection is an improper motion, so that means we have to pick the coin up and turn it over. And when we do, we will be looking at the back side. And in this case, I've chosen to show you an Ohio quarter, one that shows the outline of Ohio on the back, together with some famous events associated with state of Ohio. Now I want to observe that although we can see that the quarter has moved, if we just look at the boundary circles, if you do either a rotation of the circle or a reflection of the circle, well, you can't see that you've done anything, right? So this is exactly a symmetry, right? So these motions of rotation about the center point or reflection across an axis through the center of the circle, that's a symmetry of the circle. It's a motion which, after we're finished with it, makes the object, the circle, still look the same. Now, how many symmetries does a circle have? Well, we've already said that it has rotational symmetries and it has reflection symmetries, but we haven't said what the angles are, and we haven't said what kind of axes we can use. Well, let's ask about rotations. What sort of angle can we use for rotation that will give us rotational symmetry of a circle? Is it 1 degree, 5 degree, 12 degrees, 90 degrees? What should it be? And I hope what you're thinking is, well, it can be anything, right? We can rotate through any angle we like, however large and small we want it to be. And what about reflection symmetries? Well, what kind of an axis do we have to use? We can't reflect across a line that's somewhere off center, but if we take a line that exactly goes through the center of the circle and reflect across it, the circle seems to be unchanged. So that is a reflection symmetry. Now note, since we're allowed to use any angle of rotation and any axis that goes through the center of the circle, there are infinitely many symmetries of a circle. It has infinitely many symmetries. Now, what that means for our unit is actually that's too complicated an object, believe it or not, because of the fact that a circle has infinitely many symmetries. From our point of view, that's an awfully complicated and sophisticated object to analyze. So we're not going to think any further about symmetries of a circle. It's just too complicated. Instead, I want to think about figures that have rotational symmetry, but only finitely many rotation symmetries. And here's an example, this blue star. So it's a perfect five-pointed star, such as what you would find on the U.S. flag. Of course, on the flag, it's a white star on a blue background. Here I'm showing you a blue figure on a white background. And we can take that star, we could imagine rotating it, right? And as we started to rotate it, visibly we would see that it's changing, right? But if we rotate it far enough, suddenly it will look exactly the same as when we started. So consider, for example, the point at the very top, okay? As we begin to rotate around the center of the star, eventually that point will become the point over on the right. Again, a point of the star. Now, what angle were we rotating through there? The answer actually is 72 degrees. Now, how do I know that? Well, I know it's a perfect five-pointed star, and if I did that same thing 5 times, I would have rotated fully around. So the number I'm looking for has to be 360 degrees divided by 5, which happens to be 72 degrees. Now, it's a general fact that if I have a figure that has finitely many rotational symmetries, then the smallest angle of rotational symmetry will be a number of this same form. That is to say, it will be 360 degrees divided by some positive integer n, at least 2. In this example, the value of n was equal to 5, not very much of a surprise. It's a five-pointed star after all. N was equal to 5, and so the smallest angle of rotational symmetry is 72 degrees. Here's another example. Here is a printed letter S. Now, depending on what particular font you're using, it may or may not have symmetry. I want to use an example in which it does have symmetry. And what is the symmetry that this letter possesses? Well, it has rotational symmetry. There's a point. Let me see if I can indicate it here. Get out a little pencil here. It's right around here, very roughly. That's a point about which we could rotate. Now, if we rotated it by half a turn, that is to say 180 degrees, the points here at the top would become the points at the bottom, but in fact, the figure would look exactly the same. That printed letter S would look exactly the same. So here, n is equal to 2, and the smallest angle of rotational symmetry is 180 degrees. In this special case, we often say the figure has half-turn symmetry, right? We can do a half-turn, and when we're done, it looks the same as when we started. Now, here's a definition. A plane figure having only rotational symmetries is called a cyclic rosette. Again, a cyclic rosette is a plane figure whose symmetries are just rotational symmetries and no others. Now, here are two examples, the star and the letter S. Which one of these figures is a cyclic rosette? Well, it's the letter S. The letter S has just that rotational symmetry. Why is the star not a cyclic rosette? Well, besides having rotational symmetries, it also has reflection symmetries. You see, I can draw a line here. I'll do this very crudely. But right about here, you can see that there's an axis of symmetry. In fact, there are others. There's another one here, and so on. There actually are several. Again, I'm drawing it very crudely, but we can see that it has reflection symmetry. So that star doesn't just have rotational symmetries, it also has other symmetries, so we don't call it a cyclic rosette. However, the letter S, as I've said, is a cyclic rosette. Here's another example. I just took this photograph one day with my phone in Pennsylvania at a Pennsylvania Dutch festival, and that is a cyclic rosette. That is to say, it's a figure that has only rotational symmetries. The value of n here is equal to 4. Now, I'm a little hesitant to mention it, but this looks an awful lot like a political figure that also has this same type of rotational symmetry. It is itself a cyclic rosette, and I'm not going to draw that for you because it's such an obnoxious symbol, a symbol with such horrific associations that I think I will just say what the name is, and it is a swastika. A swastika is a cyclic rosette. It's unfortunate that that figure has now the associations that it has and will always have. It's actually, without that association, it's a beautiful decorative object. For example, if you ever go to Mexico or Central America, you'll find, perhaps to your surprise, that it's used on decorations. And this is in pre-Columbian kind of artwork. And of course, it's entirely free of the Nazi associations that we have with it. All right, let's work out an exercise here. Here are the instructions. For each figure here, draw all the axes of reflection. Also indicate each center of rotational symmetry and write the smallest angle of rotation. Now, I hope that you find this picture somewhere in a packet of handouts that you have printed for yourself. In fact, if you haven't done that, please print that out now, and I'm going to ask you pause this video now and do that exercise. And then when we restart, I will review the answers. Okay, now I'm going to assume that you did work this out, and let me go through these one by one and talk about the axes of symmetry and the centers of symmetry and these angles that we're looking for. Now the first one here is this propeller that I'm now circling. And you may have been tempted to look at that one and think that it has some axis of symmetry. But in fact, those blades on the propeller do not themselves have symmetry. You see, there's a certain direction of rotation for this propeller. And because of that, those blades are not symmetric. So there is, in fact, no axis of reflection. The only thing we can draw here is right here in the center somewhere. We can say that there is a center of rotational symmetry. And the smallest angle of rotational symmetry is 360 divided by 3. That's 120 degrees. I'm printing that very crudely there, 120 degrees. Okay, we move on to the letter B. Now this has no rotational symmetry, but it has reflection symmetry, and there's the axis. Okay, so the only symmetry it has is reflection symmetry with a horizontal axis, as indicated. Okay, here's the key, and that key that we've been using in many of our previous exercises itself has no symmetry. So there's nothing to draw, there's nothing to write. It doesn't have any axes of reflection. It doesn't have any centers of rotational symmetry. There is no smallest angle. The letter S, as we've already said, is a cyclic rosette. It just has rotational symmetry. Right about there is the center of rotational symmetry, and the angle is 180 degrees. Okay. This pip, as it's called, from a playing card, a spade playing card, has just reflection symmetry. There would be an axis of symmetry, now a vertical one rather than a horizontal one. No rotational symmetry. The next object is certainly the most elaborate looking one that we have here. This is actually an object that comes out of another part of mathematics, which is called a Julia set. And maybe you were thinking you could find some axes of symmetry here. It's kind of tempting, but for example, if you think that there is, say, an axis of symmetry going from upper left to lower right, well, look again, because it doesn't quite have reflection symmetry across any such axis. In fact, all it has is rotational symmetry about a center point, right about where I was just scribbling. In that sense, it's very much like the letter S, right? All it has is half-turn symmetry. The angle is 180 degrees. Okay, the letter A is like the club pip. Did I say spade earlier? If I did, I meant to say club. And there is the axis of symmetry. The letter F is asymmetric. Finally, we come to these last two, and these have both reflection and rotation symmetry. Now, I'm probably going to draw this awfully crudely, but here is an axis of reflection. But here's another one. You don't want to think that there's just one. Anytime that I take a midpoint of an edge, I can connect it to the opposite vertex, and that is an axis of symmetry. Okay, so there are actually 5 axes of reflection symmetry. Also, this has rotation symmetry, so maybe I should scribble in here a bit more to indicate that here is the center of rotational symmetry. And what's the smallest angle? Well, it's 360 divided by 5, which is 72 degrees. Finally, the letter H has two axes of reflection, both horizontal and vertical. It also has rotational symmetry, and the smallest angle of rotational symmetry is 180 degrees. Half turn. More vocabulary. A dihedral rosette is a plane figure having both reflection and rotation symmetry, but no other sort of symmetry. Now, at this point, you're not likely to think of any other kind of symmetry that an object could have, but I just wanted to say it for completeness. So what's the difference between cyclic rosettes and dihedral rosettes? Well, for a cyclic rosette, its only symmetries are the rotations. For dihedral rosettes, both the rotations and reflections. Now, for a dihedral rosette, it will turn out that all the rotations have a common center, and all the axes of reflection will go through that point. So let me show you that here. Again, very rough drawing. Here are axes of symmetry. There are 5 of them, and they all go through a common point, which I'm not managing to show very well. There is actually a common point where all these lines are supposed to be meeting, and I've just done it very terribly. It's right about there. All those lines I drew should have gone through that point, okay? The rotations have a common center, that point, and all the reflection axes go through that same point. Here's another example of a dihedral rosette. Again, I took this photograph in Pennsylvania at the Kutztown Folk Festival. And this is a wonderful example of something that's called Scherenschnitte, which is an art of cutting elaborate figures out of paper with scissors. Okay, that's what's been done here. This is a single piece of paper that has been carefully carved with scissors into this beautiful shape. And you'll observe that this is a dihedral rosette with n equal to 8. That is to say, the smallest angle of rotation is 45 degrees, and it has lots of reflection symmetries. Now, as a matter of fact, if you notice, I could cut out the center portion. I'd hate to do that to this beautiful figure, but just imagine doing that. If I cut out that central portion, I would then have a dihedral rosette with n equal to 16. All right, to finish up here, let's do one more elaborate exercise. It's based on the same picture as before. And what we want to do is to identify each figure as one of the following, either a cyclic rosette, or a dihedral rosette, or not a rosette. For those that are rosettes, we should specify the value of n. Now, just for simplicity, I'm going to write either C or D or N on each one of these. The first one, the propeller, is a cyclic rosette. The propeller is a cyclic rosette, so I'll write a C here. And what's the value of N? N is equal to 3. Okay? The letter B doesn't have any rotational symmetry, so I'll just say it's not a rosette. The key is asymmetric, so I say it's not a rosette. The letter S is a cyclic rosette, and N is equal to 2. This club pip is not a rosette because it doesn't have any rotational symmetry. The Julius set is a cyclic rosette. I'll write a C for that. N is equal to 2. Letter A is not a rosette. Letter F is asymmetric, therefore it's not a rosette. The pentagon is a dihedral rosette. That's our first example of that. I'll write a D right in it. And N is equal to 5. And finally, H is also a dihedral rosette. It has both reflection and rotation symmetry. And the correct value of N is N equals 2.